This presentation is delivered by the Stanford Center for Professional Development.
Okay. Let's get started. So, today's movie segment is about a special actuator. Probably you saw this on the first lecture, but we will see some more details. So this is a flexible actuator that comes from Toshiba. And this was developed in the early 90s. It was presented at 1991 video proceedings.
This new actuator is made of fiber-reinforced rubber and is driven pneumatically or hydraulically. It has 3 degrees of freedom: pitch, yaw, and stretch, which are adequate for robot mechanisms such as fingers, arms, or legs. The actuator has 3 internal chambers, and the pressure in each can be controlled independently through flexible tubes. The rubber is circularly reinforced with fiber to resist deformation in the radial direction. The actuator can be flexed in every direction by controlling the pressure in each chamber. I've developed actuators ranging in size from 1 millimeter to 20 millimeters in diameter. This is the 4 millimeter actuator. The design is easily miniaturized because of its simple structure. This is a modified version. The rubber is reinforced spirally with fiber so that rotational movement is possible. We can apply these flexible microactuators to miniature robot manipulators. By connecting them serially, we get an arm with many degrees of freedom and snake-like movements. This is a prototype consisting of 2 actuators and a mini gripper. It has 7 degrees of freedom, including the gripper. It can accomplish delicate tasks, which could be handled only with great difficulty by conventional robots. Constructing miniature robot manipulators is easy, because the actuators also act as the robot structure. On the other hand, combining the actuators in parallel results in a multi-fingered robot hand. They form a dexterous hand with a delicate touch. This prototype consists of 4 actuators, each 12 millimeters in diameter, and it has 12 degrees of freedom. It is able to handle fragile and complicated work with ease, because the actuators deform to suit the shape of the workpiece itself. A bolt is easily tightened with only rough settings of the position and orientation of the hand, because the actuators have such good compliance. Miniature robots with a soft touch and no conventional links can be created using these actuators. We foresee the use of flexible microactuators.
So, what do you think? What would be the advantages of using pneumatic in this way? Yes?
Probably safer for a lot more objects.
Safer, you said, or safer? So safety is a very, very important aspect of the design of a robot, especially if the robot is going to interact with the humans. And you really don't want this robot to just go crazy and hit and make a large impact. So soft actuation using pneumatic is very good because it basically it's compliant, right? Now, another implication of the fact that you are using pneumatic is the structure of the robot is going to be lighter. Because if you think about operating these fingers with the motors, or if you think about an arm with motors, you need to carry the motors, you need to put gears, you need a lot of structure to handle it. So definitely this is lighter, safer, more flexible, compliant, all of that. Any disadvantage you can see? Yes?
Harder
Yeah, basically, well, I mean, depends what you want to achieve, but you can not expect to achieve all the tasks. What kind of task you cannot control with this type of actuation?
Maybe precise motion.
Precise motion or fast dynamics if you want to change directions, and because what is the problem with the actuators? Yes. So yeah, I mean basically the response of the system is slow because you are using air pressure, and you cannot push the air pressure to a point where you can really get fast dynamics. Well, later on in the quarter, we will see a concept that combines this idea of using pneumatic, which is light to carry, and would result into a nice light structure, combine it with other type of actuation to bring hybrid actuation in a way that combines both the advantages of the light structure and the fast dynamics that we need to achieve all the different tasks that would require the robot to respond quickly. Yes?
Is there any good way to close the loop on the movement? Like, you don't actually know where you're
the last sequence, you would see the robot was like turning.
Yeah.
Okay, well, okay, anyone would like to answer this question? I'm sure you have an idea, but I mean, this is really not fundamental to the robot design. It is more on the fact that we have no external feedback or no touch, or we are not using the information about the touch to realize that we already left that contact. But this is actually something that you can add on top of the design to, like, with what kind of sensor you would use.
Pressure sensor?
Touch sensor? Yeah, you mean like you want to know if you are touching or not?
Right. I mean, pressure would be, I guess, since like for a rotary joint, you got an encoder, so you know exactly like how far you are. But with something like that, like, the curvature is going to change depending on what it's touching and everything. Like, yeah, you could put something that exactly tells you the position of the end.
So we can put a sensor at the end that is localized at the tip of the finger, and then we can feel whether the sensor is on or off. That is just touch. But if you want more information about the pressure, you need a sensor, the tactile sensor that would measure. But then the problem, I mean, now we come into a much harder problem, which is the fact that if you're holding something, let's imagine with your two fingers you're holding something, and there is always slip. So you need to measure the slip so that you can apply larger pressure. And to do that, you need sort of dynamic tactile sensing. So there has been a lot of work actually in the group of Mark Katkowski, a lot of research on tactile sensing, dynamic tactile sensing, and also the idea of using pressure is a very good idea because, in fact, by measuring the pressure and the control pressure, if there is a difference between what you are expecting and what you see, you will be able to deduce some information about the contact. There was a comment here?
You could put stretch sensors on the surface and use those to find the position. Yes.
Mm-hmm. Now, if you instrument the environment, obviously you will be able to get a lot of information about the environment, but that is costly. So you want more to put the sensors on the robot. But there is another type of sensor that will give you more information about the environment, that especially about whether you are close or not, or like to localize and see where things are. To see where things are, to see. What do we use? Vision. Put a couple of cameras and you would see where you are with respect to the world. And so you have a mechanism, you have the controllers, but really you need to close the loop. But to close the loop, you need perception. And perception could use sensors in the environment, external that are monitoring the environment, or instrumentation on the robot itself. Anyway, this cute design actually was pursued for a couple of years. They built even a big robot that is walking with those legs. And I'm not sure if we will see it, but then this project didn't go any further. It is like many of the designs that make use of air pressure only, you end up with really limitations, a lot of limitations on the use of, on the ability of the robot to perform tasks. And in fact, there is a lot of work today in this area that is with artificial muscles to create faster muscles that use air pressure, and there are many different solutions that will push this a little further, but still you have limitations. And as I said, we will discuss a little bit more about those issues of design, especially in the context of safety, because safety really is becoming a very important aspect in robot design, because we have been working mostly with the with industrial robots. So industrial robots are working alone or working with parts and objects. You don't really worry too much if there is an accident just between, the robot and that environment. But if you are going to work with the humans, you really have to make sure that there is no danger to the human, and that is really a challenging problem. So we will come back to this later. Any other comment about this? Okay, all right, so let's go back to the lecture. So last time we saw this tool we call homogeneous transform, and the homogeneous transform really has several interpretations, or can fulfill several functions, and the first one of them is the fact that transformation like this allow us to describe the frame. So frame B is described with respect to frame A given this transformation. So if I know the homogeneous transformation between B and A, that is this 4x4 T matrix that describes B with a relation to A, then I have a description of this frame B. And this description contains the rotation of the axis of frame B with respect to A, and the location of the origin of frame B with respect to frame A. Now, we saw also that there is another role this homogeneous transformation can play, and the second role, or third role, whatever. Do you have an idea what can we use this transformation for? What can this transformation help us do? Yes? Operations, that is, we can interpret the transformation as an operator that is acting on a vector and changing this vector, rotating the vector, or rotating and translating that vector. So this is a second interpretation, the transformation as an operator. Or, one more. So if you have a vector in space described with respect to some frame, B, and you want its description in a different frame, A, can you use this transformation? Right? So this is the mapping, what we call mapping. That is, we take a description of a vector P in a frame, B, and we map it to a description in frame A. So the vector P, this green vector over there, is now the red vector, that is this one, describing this point in frame A. And you can see here we have two different vectors. If there was no translation, then basically it will be the same vector with two different set of components. And as you said, we have also the description of the homogeneous transformation as an operator. That is, we take a vector P1 and change it to a vector P2. So the vector P1 is now P2 after this translation. So these different roles of the homogeneous transformation use the same mathematics, but the application, the interpretation is going to be different, and we have to pay attention to the way we apply that definition. So the next question that we have to address is how we now use. So if you remember, when I talked about homogeneous transformation, I said by building this matrix, 4x4 matrix in a higher dimensional space, we are able to have a homogeneous relation between vectors. So this property is going to help us propagate and go from one frame to another and have descriptions that are related by the individual transformations between frames. So here is an example. You have this camera monitoring the environment, and here in fact you have a robot, a mobile manipulator. This is Romeo. That is did I introduce Romeo and Juliet to you? No, not yet. Okay, well, maybe we'll have a chance a little later. So Romeo is essentially a mobile platform, holonomic mobile platform with an arm. And it allows you to move in the environment and manipulate the environment. But because of the platform, this is done everywhere in the world, not like when you have just one arm fixed on a table where you bring material to be processed. Here you are able to explore the human environment. And in fact, the robot is moving and its location is always difficult. So the question is, how can we, for instance, locate this robot? So you need to find actually the transformation between the base frame of the robot with respect to the camera. This is a little bit difficult unless you are able to, well, to find elements and different things. So suppose the camera is monitoring the end effector. So you have the end effector here and you can see it. So if you have this relation that is in a given frame, you are able to see and identify the end effector, which is, let's say, this frame. Then through the other path that is going from here to the base, through those transformations to the end effector, you have another path. You know this, and you know this, then you can compute this. And we need to be able to propagate and resolve this transform equation. So this comes everywhere. Yeah, well, Romeo is capable of ironing. I will show you maybe later if we have a chance, a little time in the lecture. Again, where you are ironing, where is the base, and you have this loop in the environment if you are observing the environment, and you need to be able to go through the transformations. From the base to the end effector, you have always the forward kinematics through all the transformations between links. But obviously, with the ground, you have slippage, and you cannot determine exactly the relationship between a fixed camera and the location of the base. So first of all, how we combine transformations. Let's consider two frames and consider that now we're going to introduce a third frame, C. So we have a transformation from C to B. We have a transformation from B to A. And obviously, I'm interested in the transformation from C to A, the total transformation. I would like to combine these two transformations. So if we have a vector described in C, that is, we have a point P described in frame C. The question is, what is the description of this vector in frame A? Well, the result is obvious. I mean, probably you already get it. We are going to multiply these two transformations. And to prove it, let's first compute what is the transformation to frame B. P in B is simply going to be obtained by the homogeneous transformation from C to B, right? Now, if we write the same thing for this point in B, we can go to A through the homogeneous transformation B to A. Now, if we substitute this with the expression that uses C, we will obtain this relation. That is, the vector in C is transformed into the description in frame A using this form, which means that essentially we are going from description in C to A that is from C to A. And that means essentially the transformation corresponding to these two frames, successive frames, is going to be the product of the matrices, the homogeneous transformation C, B, and B to A. And you can see this has a nice form. You just eliminate the B, and you're going from C to A with this notation. So that is really the advantage of homogeneous transformation, is that you have a matrix, and then when you have multiple frames, all what you need to do is to multiply these matrices. So now if we multiply C to B, B to A, this is what we will obtain. We will see here that the structure of this transformation is going to maintain the structure with respect to the rotations. So we have the same properties of rotation. It is C to A through CB and B to A. And this vector, which is the origin, the vector locating the origin of C with respect to A, well, it is essentially computed by locating the origin of C with respect to B, rotating it to the right frame, and then adding the offset due to the origin of B with respect to A. So, the logic is very simple. It's vector computation, but again, when you do the multiplication, it is automatically taken into account and you get those results. So now that we have this relation that would allow us to combine two rotations, we can go and do the transform equation. The transform equation is this equation that is going to let us extract some information, given that we know some other information about relationship between frames. That is, the robot base is fixed at a given instant. The end effector position could be computed with respect to this base. Now, if we know where the end effector, and if we are able to have that total relation, then we can compute where the base is. And in this relation, there is some very intuitive property about this fact that if you start from A and go all around, walk all around and come back to A, you should obtain a transformation, a homogeneous transformation that is equal to identity. So we have an identity transformation when we walk from A and go all around and come back to A. And using this, we can say essentially from A to D, D to C, C to B, B to A, if we multiply them, be careful with the order. You're going to eliminate all of these and you get A to A, which is identity. So now, I don't know, what is missing? Let's say we are missing D to C. Then you multiply by the inverse of this from one side and the inverses of the others, and eliminate and compute the transformation that you need. That is, here we have 4 transformations. One of them is unknown. Then you can extract it and find it. In the case of computing A to B, simply you are going to find that you go from A to B by A to D, D to C, and C to B. Okay? So just, and don't be confused. I mean, sometimes the transformations are not written in the right direction, so you will use the inverse. But you have to walk in the same direction, and then you can say identity A to D. And then you can compute any element that is unknown. Okay. Well, we're done with transformations. Any questions about transformations? Good. Well, I think you have a homework about that, so hopefully you will find out if you have questions. All right. Well, now we are then at the last point in spatial descriptions, and this is the representations. So what do we mean by representations? The questions that we're concerned with is this question. We have this end effector, and the end effector is really the purpose of the whole manipulation problem. That is, we are concerned with how to position this end effector in space and how to move it to some location. So we need to say, well, our end effector is at some location X, Y, and Z, and it has some orientation. Now, it's not enough to say, well, I have a homogeneous, because this description we know. We know the position and orientation. It is embedded in the homogeneous transformation. We know the relationship from the end effector to the base frame through T, and you're going to find that relation. When we finish the forward kinematics, when we complete the forward kinematics, you're going to be able to say my end effector transformation with respect to the base is given by T. And this T will come from the description of the manipulator, so the link length, the angles of tilting and characteristics of the links, and also it will be function of what? What other parameters will be involved in T? So here is the manipulator. It's moving. At this configuration, how can I compute this position and orientation? I'm going to use this length and the angles, and also I'm going to use, come on, I'm tired here, lift this. The joint,
Angles.
the joint angles. I need the joint angles. So what is variable? What is changing as I'm moving? So T is going to be function of coefficients that are constant depending on this manipulator and the joint angles. So T will vary with joint angles, right? So the configuration of the robot will affect where this end effector is going to be. So we will be able to find the T as a function of the joint angles, and it will be a matrix 4 by 4. And this matrix will contain, for each configuration, the description of the homogeneous transformation. Okay? So at a given configuration, we measure the encoders, we read the encoders, and then we can compute T and say, my homogeneous transformation for the end effector is this. Now the question is, where is the position of the end effector? And what orientation the end effector has. The question is important because I'm not only concerned about positioning the end effector, I'm going later to move it following a trajectory. I need to think about the velocity. So I need some description of coordinate that would give me like coordinate x, then I can compute x dot. eventually acceleration. So I need a set of coordinates. Okay? So what we need to do then is to extract from T the position description and the orientation description. And say, I have a description, something like, I don't know, I have the position and I have the orientation. I have a set of parameters x, xp for the position and xr for the orientation, right? Because I cannot take t and take the derivative of t and just say, well, I'm going to build a trajectory directly with t. You understand? All right. So where can we find xp? What is the where is the information about xp in T? The first three elements of the last column. That's what you said? Correct. Because this is going to give you basically this vector. This vector is in the transformation on the last column of T. So you can compute this point. And that would be a description x, y, and z of the effector position. Where is the orientation? At least where I can find information about the orientation in T. Yeah, so it will be the first three columns corresponding to this R matrix, the rotation matrix in T. Okay, now how should I represent X? Because you said X, Y, and Z, but there are other possible representations. So for the position, I could say I take that position and it is represented by X, Y, and Z. So this is the Cartesian representation. But I can select these angles, theta, and the projection of that on the plane xy, and come up with a cylindrical representation. Or I take that other angle and come up with a spherical representation. So there are several ways of representing that position. And most of the time we will use Cartesian coordinates. But in cases like if you have a dexterous manipulation with a tool and you want to move in this direction, it might be more advantageous to use cylindrical coordinates, because your task is aligned directly with that vector and you can just extend the vector and move, and the angles are fixed, so you control them and just you move along that vector. So other representations are also very useful in different tasks, for different tasks. Okay, well, still in here we're talking about x, y, and z, rho theta z, r theta phi, always three parameters, three independent parameters. So not much of fun, simple. The fun starts when we think about rotations, and that is where most of the difficulties with the kinematics of robot systems lies. In fact, we're going to start to see some aspect of those problems, but those problems will carry on all the time as we start to consider instantaneous rotations, instantaneous accelerations, and their relations to the representations. The space of rotation is really different from the space of linear motion. That is the space where we describe a position. And we're going to, little by little, see this problem. So the first complete representation that contains all the information about rotation is our rotation matrix. So in this rotation matrix, everything is there about the orientation. I have an object held in the end effector. basically there is a frame x, y, and z that is going to rotate with this object. And if I take x, y, and z frame and take its component with respect to the reference frame, that will be my total rotation. So from T, the homogeneous transformation, I can extract this rotation matrix, and in which I see that R1, this is a vector, these are the components, R1, R2, R3 are these three vectors. So R1 is what? In this frame, if I take the x axis, R1 represents what? What is the definition of the basic definition of the rotation matrix? We say that the first column is the component of x on the base frame. So R1 is really the component of x. R2 is the component of y, and R3 component of z. Okay, now I can build a representation with this. I can just say my XR, this x that is going to represent the rotations and the orientation of the end effector, is simply the concatenation of R1, R2, R3. I take the three vectors and put them one on top of the other, R1, R2, R3. It's a long vector, but this vector actually contains everything you need about the orientation. Now, obviously, we're overdoing it. So, do we need 9 parameters to represent the orientation? Obviously, there is, how many degrees of freedom we need? How many parameters, the minimal number of parameters would be? 3. I mean, we have 3 degrees of freedom in orientation. But here we have 9. So how come? How come we have 9?
Well, each one of those vectors is a unit vector, so the third component is already predetermined.
Okay, so we have sort of 3 relations of normalization associated with R1, R2, R3. So this is 3 constraints. Good. We need more. 9 minus 3 was still 6. I need 3 more. Yes?
Each of those vectors is also perpendicular.
Uh-huh. Okay, so R1, R2, 1 constraint, R2, R3, 1 constraint, and R3, R1, 3, 6. Good. Let's check. Yeah, you're right. So 6 and you have 9, basically you have actually 3 degrees of freedom. Now, this is a redundant representation. Redundant in the sense that the parameters we are using are not independent. And that creates a problem. That is, you cannot say, so what is the problem with that? I don't know if you realize the problem. Think about motion. I'm going to take this and rotate it like this. I mean, I'm going to just put some water in the cup. So you have a motion. So you have some initial XR, you have some final XR, and you want to go from one to the next. How can you create a trajectory? You see the problem? So, okay.
There are multiple solutions. Or
Well, let's think about the simpler problem, which is I'm going to move from A to B. A is defined by X A, X, Y, Z A, and here X, Y, Z B. How can I move from this to this one? So X is equal 10, and XA is equal 10, and XB is equal 22. So
slope and try
Yeah,
it?
I can interpolate, and every point is valid. Okay? Now let's interpolate XR1, I mean the first configuration and the final configuration. If you do the interpolation, you will violate those constraints. If you just do linear interpolation between the two, you cannot take that. They are not independent, so you have to monitor what is happening. So it's very difficult to just work with this directly as X, Y, and Z. What is happening with the rotation is that you are moving over a sphere, SO3, in that space, whereas X, Y, Z are moving in the free space. And you have to deal with these constraints. Okay. So what other representations we have? Oh, come on. Yeah, you know them. So if we don't use the vectors associated with the frames, what can we say about the orientation? There are these angles, right? What angles? Euler angles, exactly. Euler angles are very, very useful. Now, there are many different ways, in fact, of talking about an angular representation. The three angle representations, I mean, you can count maybe 24 of them. We distinguish between Euler angles, the fixed angles that we use in aviation, and each of them has like sort of 12 different representations. And those representations come from the way we obtain these angles. So you have a frame, and you're going to try to find the frame B and the relationship between the two using three angles. So what do? You have many options. You can go to this axis and rotate about this axis first. And then once you rotate about this axis with some angle, then you can go and rotate about this one. And then after, you can come back to the same axis and do the rotation, or you go to a third axis. And so you have, and maybe you can start from the y-axis first. And so that's why you have a lot of different ways of doing it. All right. But you end up always with three angles. But you need to know which axis you're rotating about. And whether after the first rotation you rotated about the first axis, there is no problem. You get some intermediate configuration. But next you can rotate about the new axis that resulting from the first rotation. So this is like relative rotation with respect to the frame created after the first rotation, or you can maintain your rotations, three rotations about fixed axes. So we distinguish between fixed rotations, fixed angle rotations, and that gives us 12, and relative rotations give us another 12. Euler angles are the relative ones, and the fixed ones are what we call fixed angle rotations. Okay, so let's start from the beginning. I'm going to go to this configuration by first putting the two frames together. Okay? All right. Let's rotate. I'm going to rotate about the x-axis with some angle. This is the first rotation. The new frame that results, so the idea is I'm going to rotate from A, identical, and then I'm going to get a first frame, and then I will do another rotation and a third rotation to reach the final B, the B which is in here. Okay. So if the next rotation is done about the relative next axis, y. So from that b prime, I'm going to do another rotation about b prime. Then this is sort of Euler angle representation. And I have 12 set, depending on the selection of axes. If we do this next rotation on the blue axis, the fixed one, here I will obtain an intermediate one, but when I continue, this will give me the fixed angle rotations. And you have 12 sets. Now, we will see that, in fact, every representation here has an equivalent representation here. So in total, we do not have 24 different representations. We have only 12 that could be represented, obtained from relative axis or fixed angle axis. Okay? So in total, you have only 12. All right? Let's take an example. I'm going to take the rotation z, y, x, which means we will start with a rotation about the z-axis, then y, then x. And I'm talking about Euler angles, which means relative rotations. So here is the first rotation. You're rotating about the z-axis, and the xb prime and yb prime are in the same plane as xa and ya. And you have an angle alpha between those axes. So the next rotation will take place about what? About y. So, and this is the new y that resulted from the first rotation. And we will call it beta angle. And now this rotation is in the plane xb prime and zb prime, right? And the final rotation will be about x, and it will be of an angle gamma, and it will be in the plane yb double prime, zb double prime. And that will take us to B. Now, I need to compute this transformation, and I need to compute what is the rotation from frame B prime to frame A, the transformation from frame B double prime to B prime, and the final transformation from B to B double prime. And if I have those transformations, if I multiply them out, I will find the total transformation. Good. So that is what we want. We want to compute this, multiply them out, you get B to A. Well, maybe before. So what was the last transformation? Was x, rotation about the x with an angle of gamma. So I'm going to write rotation about x with an angle of gamma. Rotation, the one before was rotation about y with the angle beta, and rotation about z with an angle alpha. You have your transformations. So you take these. So this is what? This is 1, 0, 0 cosine the angle gamma minus cosine sine cosine, and you have your transformation, you compute it, and you find your rotation. So you get this transformation as a function of alpha, beta, and gamma. And now for a given orientation, you know the position in rotation space, you say it's alpha, beta, gamma. Now if we do it with fixed angles, essentially we are going to do a rotation about x, about y, about z, but those angles are done, I mean these rotations are done about the fixed axis. In fact, this is what we call the roll, pitch, and yaw, and these are used in aviations because you're doing small angle rotations in general, and these are very intuitive to perceive what rotation you have made. And the computation of these comes to be very simple, because if you think about the rotation x with the angle gamma, that first rotation, if you have a vector v, this vector is transformed by the rotation about x with this angle. You have an operator changing the vector v to the vector rx gamma v. And with the next transformation, you take the result and transform it with rotation about y. And the last one is going to apply the last transformation. And when you put all these transformations, you see that the total transformation is given by the product of x gamma, ry beta, and rz alpha. So these operators that we saw before are very useful. And in fact, when we look at those transformations, essentially we are going to obtain the transformation directly from rotations about directly those axes. So those operators are very simple because they are done about the x, y, and z, and every one of them is like the operator about z is a rotation here, 0, 0, 1, about the z-axis with cosine, minus sine, cosine. The operator about y is rotation about the y-axis with this angle, and this is the rotation about x. So if we do this multiplication, you will obtain a matrix that is only function of alpha, beta, gamma. These, I'm not showing the terms because they are a little big, but basically I'm showing just those elements. And you can now do the product and find that matrix. And now your rotation matrix is expressed as a function of alpha, beta, gamma. Now, let's go back to the beginning. How do we compute the end effector position and orientation? How do we measure it? We said we measure the encoders. We use the forward kinematics to compute the homogeneous transformation. And we know the rotation matrix numerically. Now what we are saying is this matrix is equivalent to this matrix computed with those three rotations. So how can I find those rotations? What is alpha? What is beta? What is gamma? This is really the problem. The problem is I need to be able to compute these values, and to compute these values I need to find the inverse that is given the value of the matrix. I need to compute those values. Oh, this is another example here. So here we have z, y, x. The matrix looks like this. If you have z, y, z, you get this other matrix. So these the elements that are very simple. So you know this element cosine beta, you have the numerical value, and you identify it cosine beta, and you can invert beta and find what is beta for that specific configuration. Okay. So if we take ZYZ representation, what is the angle here? Euler angles. ZYX. So what is alpha, beta, and gamma? Don't check your notes. Have to remove these. Can you think about it from here? Can you see it? What is the which one is non-zero? I mean, I'm sure most of you saw the answer already, but can you see it? Really? So this is a rotation. We went to the red frame from the blue initially with a rotation about which axis? the x-axis of an angle of plus 90 degrees. Yeah. Good. You see it. Everyone? No confusion? Good. Okay, as I said, if we take fixed angles and we take Euler angles, I'm writing them together now. The fixed angles, this is the relation we obtain. The Euler angles, this is the relation. And now, if you look at the two, you can see that the rotation about Euler rotation and fixed rotations are identical. That is, the x, y, z with those rotation gamma, beta, alpha is equal to the z prime, y prime, x prime with alpha, beta, gamma. So for each rotation, you have a corresponding rotation in the 12 sets of fixed and Euler angles.
So gamma, alpha, and beta are the same for both? Or are they different?
No, the same. In the same equation, they have to be the same. All right, so now we come to the difficult problem. The problem I mentioned earlier, which is that how you obtain these alpha, beta, gamma, how you obtain your representation from your measurement. So you are given the rotation matrix numerically from your forward kinematics. So you know R from B to A, and the question is, what is alpha, beta, gamma? Well, I mean, essentially, I need to identify each element from B to A, so I know R11, R12, R13. I need to identify them to the rotation matrix. So now you have the full matrix, and you have 5 minutes. So how do we do that? I can help you if you need some help. All right. Obviously, these terms are a little bit too complicated, this one and this one. So let's see. I have alpha, beta here, and beta here. So I could use these, right? So how can we compute beta? If we square this and square this, cosine square and sine square add to 1, and I will get cosine beta square, right? So I can get cosine beta from the square root of this element and this element, right? Now we're going to use a function that we call the inverse of the tangent 2 that takes two arguments. It takes the sine and cosine to compute the tangent. And that gives you all the angles within their area. So where can we find the sine of beta? Well, we have the sine of beta here in this element 3, 1. It is minus, so it has to be minus. So if I take this function and I place this here and here, I can obtain beta. Now, given that you obtain beta, how can you compute alpha? Well, you go back to those elements 1, 1 and 2, 1, and you know beta, so you can compute the cosine and sine. The problem that you're going to have is this problem, which is that if your cosine beta becomes equal to 0, if cosine beta becomes equal to 0, you're going to have a problem. And this problem is that you cannot divide anymore by 0, so you have some indetermination, and this leads to a singularity. We call it singularity of the representation. We will see later kinematic singularities, real singularities. The robot is moving, and when it reaches this configuration, the robot cannot move immediately in this direction. It's locked in this direction, like this. This is a kinematic singularity, and we will see this when we take the derivative of the forward kinematics. But in here, this representation is fictitious. It's only you who selected this representation, that you selected a mathematical model that fails at some configurations. So in this case, when cosine beta becomes 0, you can only determine the sum of alpha and gamma, or alpha minus gamma. And the reason is, when beta is 0, essentially the z-axis are aligned and you have a rotation in the same plane. You do a rotation of alpha, then 0 and gamma. So you are not able to distinguish between the alpha and the gamma. I think I have an example. So this is what happened. If cosine beta is 0 with the sign of beta positive or negative, the rotation is done in the same plane, and all what you have is the alpha minus gamma at that location, or the alpha plus gamma if the beta is negative. So what does it mean? And why it is a problem? I mean, obviously, wow, you see it mathematically, but why this is a problem? Okay. So you are going to use your parameters alpha and beta, and you're trying to identify alpha and beta as you move, because you are measuring, and you reach this configuration. You have an undetermination, and at that moment you are not able to compute the velocity associated with alpha, as we will see that the Jacobian, when we take the derivatives, we have a singularity in that location, and you are not able to track your motion. So you cannot really determine the properties of the motion at that point. And this is a problem if you want to move and produce smooth motion. Usually, if you are doing a very tiny motion, you might be able to select alpha and beta so that they will never go to 0 within that small motion. But if you are performing large motions in space, you are going to run into the singularities. Now, we can change representation, we can use another one, but every single representation that uses 3 parameters is going to run into a singularity. All 3 parameter representation will have a singularity somewhere. And that is the problem. So 3 angle representation are efficient because they are minimal, but they have a problem with the representation in terms of the singularity of the representation. Direction cosines are perfect in terms of the representation, no singularities whatsoever. However, you have redundancy, and you have to handle all these constraints as you plan your motion. There is another derivative representation that we can talk about a little bit before talking about the best solution. And this is a representation that you can think about just by going back to the problem of moving from one frame to another frame. So you have frame A, you have frame B, and you can show that there is always a vector K about which you can rotate with an angle theta to go from A to that specific B. So there is a rotation about a vector that will take you there. So we can now think about a representation that uses K and theta. And this is the equivalent angle axis representation. So how can you build a representation? You can say, I'll take theta in radian, I take the vector K. I need to identify K, obviously, but I can find Kx, Ky, and Kz, and then scale it with theta in radians, and that will give me 3 numbers representing my position, and now I can, oh, what is nice, you can interpolate and you can move and you can go between configurations. Now, the rotation matrix associated with this is like this. It involves both the k and the angle theta through cosine, sines, and also 1 minus cosine for this new variable. And you are given this, measuring this, and you need to identify the element kx, ky, kz, which you can do through those two equations. So you can compute your k by taking the difference and dividing by the sine of theta. And this is coming from identifying with the matrix. So, do you see any problem? Well, you have a singularity. You can divide by 0 when sine is 0. So you have, again, the same problem. So, I said 9 is too much. 3 is not going to work. Whatever we do with 3 is not going to work. So what should we do? 4. Good. Let's try 4. Well, this is what actually the Euler parameters do. They now take the same concept. I take the vector. I know I can rotate with a vector. But instead of taking the angle and scaling it, I'm going to track correctly everything. We will talk about this in advanced robotics more details about it, but just like to give you the intuition, essentially we are going to take 4 parameters. The following parameters. I'm going to take W, this unit vector, it's unit vector. And I'm going to scale it by half the sine of half of the angle theta. And then I'm going to add another parameter, which is just the cosine of half that angle. So epsilon 1, epsilon 2, epsilon 3 are just omega W, the vector W, scaled by sine of half of the angle. And the last parameter, epsilon 4, is just cosine half of the angle. Now, there are a lot of reasons, a lot of interpretations for this, but what you can see here is a lot of interesting properties that comes with that way of selecting the representation. W is a unit vector. Sine square and cosine square have very nice properties. So now epsilon is a unit vector in 4-dimensional space. That is, you have this normality condition. If you add the square of epsilons, you get 1. And that has nice properties that in the operators, and it carries to the derivatives and everything. So let me just tell you that again, with this representation, this representation solved the problem, but there are really many details related to the way we select the representation, the way we track and compute the epsilons, and when any of the parameters we are using to do the computation goes to 0, something happens. So you have to be very careful about it. And if we analyze and try to identify, you can see the relationship between the representation matrix and your measurement. And you can find that if you add the square of the diagonal, it gives you 3 minus 4, this quantity. And this quantity between parentheses is what? Is 1 minus the missing parameter square. So you can then compute this parameter, and then you can compute everything else very simply. But again, you are dividing by this parameter. What happens if this parameter goes to 0? So if this parameter goes to 0, actually some other parameters will not go to 0. And because the property I mentioned, that this is a unit vector of the hypersphere in 4-dimensional space, we have a property that shows that for all rotations, at any time, there is always one of the parameters that is equal, or equal means all of them are equal to 1/2 to build one. Otherwise, it's not possible. Or otherwise, there is always one parameter that is large enough. And then you can do the same computation using that parameter that is large enough. So the algorithm that we use is always to think about what is the largest parameter and resolve with respect to that larger parameter. So as you rotate, you are tracking the larger parameter and you are resolving. If it is epsilon1, you use this formula. If it's epsilon2, you use this formula, etc., etc. So you can always resolve it depending on which parameter is large. But here you eliminate the singularity. No more singularities. So, well, we don't have time for the quiz. What are the Euler parameters for this example? It's a rotation about the x-axis with an angle 60, sine 30. So it will be x-axis is 100, sine 30 is, do you remember? 1/2. So like this. And the cosine of 30. That's your parameters. And what is the corresponding direction cosine representation? The first column is going to be 100, and then you get the sine and cosine of the angle. All right, wow, we're done. I can't believe it. On time. Okay, so have a nice break, and I will see you next Wednesday.